This is lecture 4G1 for Calculus 1 on minimizing the manufacturing costs of a right circular can. This is a problem of minimizing the manufacturing costs by using the first and second derivatives of a function. Okay. The goal here is to find the dimensions, that would be the height and the radius of this 1 liter right circular can for which a manufacturing cost is the minimum. We're going to make some assumptions. First, we assume that only one metal is used. This may not hold true. Perhaps you use a different metal for the top and bottom of the can. But we're going to, for the purposes of this problem, we'll only use one metal. Then we're going to say that the cost is proportional to the surface area. We're not adding in any other machining or manufacturing costs. So what we're looking for is to minimize the cost of the metal that goes into making the can, really. So with these assumptions, the problem is that of minimizing the surface area of the can. So we need to write an expression for the area of the can. Okay, so here's the area. Pi r squared is the surface area at the top of the can. At the bottom of the can would be pi r squared again. And the surface of the sides is 2 pi r times h. Now we have area depending on the radius and the height. We actually can rewrite this so that it depends on radius only. To do that, we use the constraint that the can must hold a specific volume, a certain amount of fluid. The problem initially said a 1 liter can. Okay, but I'm going to continue the theme that I've tried to demonstrate in this class, and that is when you solve these application problems, use variables. Then you will have solved the right circular can for any size can or any volume of can, and you have a more general solution. We could have written it in terms of height or in terms of radius, but we're going to write it in terms of radius. Here's the idea. The volume of the can is going to be pi r squared h. This volume is going to be specified. So I'll just leave it as v, and I'm going to solve for h. Now I'll rewrite the equation for area, and here's what I get. I get the 2 pi r squared, and that's from these two terms, the top and the bottom of the can. For the sides, I had the h. I substituted this. So I get 2 pi r times v over 2r squared. It can cancel one of those r's and the pi. And here is the expression for the area of the can. So this is the area of the can in terms of radius. Right. I want to choose the radius that minimizes the area of the can, and everything will fall out from there. The height will also be given because I've sort of folded the height into there, hidden it in a sense because I'm using a specific volume. To find the critical point, we're going to look for places where the first derivative either doesn't exist or is 0. Those will be our critical points. So to do that, I take the first derivative of the area with respect to r, and I get this equation. You can work through that. It's not too bad. So I get 4 pi over r squared, and in parentheses I have r cubed minus 5 minus the volume over 2 pi. Okay. So when the radius is 0, that is a critical point. However, when you have a 0 radius, you have to have a very tall can in order to hold anything in it. So we're going to reject that solution. We're going to reject that point. Okay. So then we look for places where the derivative is 0. And if you look at this, here is the, whoops, sorry. We want this term to be 0. When this term is 0, the first derivative is 0, and we are at a critical point. Okay, this is 0 when the radius cubed is equal to the volume divided by 2 pi. Right. So now we found a critical point. We do not know if this is a local maximum or a local minimum. To determine that, you could go through and plot a whole bunch of, try to graph the problem. Or, and this is what I want to demonstrate here, you go look at the second derivative. If the second derivative is positive, that means at that point, the graph of the curve would be concave upward, meaning that point would be a local minimum. If the second derivative is negative, that means the curve would be concave downward, and that point would be a local maximum. So now we'll go and take the second derivative. Here's the second derivative, but messy, we can simplify it. It's 12 pi minus this term. Right. At the critical point, r cubed equals v over 2 pi. So at the critical point, this term is 0, and the second derivative is 12 pi, which is positive. Since the second derivative is positive, the curve is concave upward at that point, and the point is a local minimum. So now I'm going to go back to my original equations. I'm going to say that the radius cubed had to be that volume over 2 pi, so the radius itself has to be the volume over 2 pi raised to the 1/3 power, the cube root of v over 2 pi. When I look at the expression for the height was that v over pi r squared. It turns out that the height is just twice the radius. Right, so the dimensions of a can, a right circular can that would minimize the surface area and hence minimize the cost of the material that would go into making it, would have a radius equal to volume over 2 pi and the cube root of that, and the height would be twice it. So whatever the radius is, the height is twice that. Or the height is the diameter is equal to the diameter of the can. This would apply for any volume v. So if we want to go back to the original problem and say we want to find the dimensions for a 1 liter can, remember you can't, you got to change liters into some kind of linear dimensions. So a liter is 1,000 cubic centimeters. So now our results will be in centimeters. Notice how we're taking the cube root of volume. So the cube root of cubic centimeters is centimeters. So the radius would be about 5.419 centimeters. The height would be twice that. And here's some graphs. Again, we were talking about using variables instead of specific numbers. If you want to draw the graph, you have to put in a value for v. So if you want to solve these equations using a specific number, then you would just have to put in the volume for v. But because we used calculus and algebra and didn't rely on a graph, we could let the volume be just v and unspecified. Again, once you've solved this with the right circular can, you could write this into your computer, you could store it as a function, subroutine, and then anytime you want to design a can of a different volume, you have your result right there. In fact, you have the result right now. You know whatever the radius is, then the height will be twice that, so you just have to find the radius based on the volume, the particular volume of the can you wanted to make. Here's a plot of that function of the surface area for the 1 liter can, the 1,000 cc can. Okay, you can see how the curve, the area gets very high if you have a small radius because you've got to make the thing really tall. Over here, you're making a very short can, but it's going to be very wide. But there is a minimum. The minimum is right here at this point. As we calculated before, r equals 5.419 centimeters. We didn't have this graph to look at. Instead, we used the first and second derivatives. So let's look at plots of first and second derivatives too. Here's a plot of the first derivative. It crosses the x-axis. It is 0 at r equal 5.419. And now we'll look at the second derivative. And the second derivative is positive here. Looks like it's probably positive. But if you remember, the whole curve, at least the portion that we showed, was concave upward anyway. So the second derivative being positive means that the original curve, the function, the graph of the function is concave upward at this point. Because the second derivative is 0, that gives it a local minimum.